Greetings, aspiring scientists, and welcome to my video today on the periodic table and periodicity. So let's go to my slides. So I think we forgot to do the guiding question of the material design section last time, so quickly, let's review that. So what role do bonding and structure have on the design of materials? As I mentioned at the beginning of that section, really they're almost everything, right? Bonding and structure in terms of alloys, it's what kind of crystal lattice and what kind of properties does it convey to the material in terms of strength, conductivity, malleability, ductility, and so on. And in terms of polymers, it's polymer length, branching, intermolecular forces, functional groups. Those kind of things have big effects on the structure, therefore on the design that we might apply to things as well. So today we'll move on to classification of matter 3.1. We're now in structure 3, the last section of structure in the SL chemistry curriculum. And this really focuses on the periodic table, which might seem strange because we've been using it so much already to do various things, but now we're sort of officially learning its history and all the trends that exist. So again, we have a guiding question for this section. How does the periodic table help us predict patterns in trends and the properties of elements? I think we'll see there's quite a lot of patterns and trends, and the main purpose of investigating them is to predict without having to go look up in a table every time, what are some properties of certain elements. Okay, classification of matter, period, group, and blocks. This is really just about the organization of the periodic table and how it came to be in the shape that it is. So this is 3.11 and 3.12. So here's a nice depiction of the periodic table I made in Claude AI, but we have different parts of the periodic table called periods and different areas called groups. So this slide that I'm showing right now has groups colored. So you can see it's kind of the columns of the periodic table. Everything up and down in one column has the same color. That is a particular group, and they have numbers as well. They're numbered at the bottom of this image. So grouped elements, one important thing about them is that they have the same number of outer shell or valence electrons, and therefore similar chemical properties. They'll react similarly with other chemicals because they have the same type of electron structure. On the other hand, then we have the periods. This goes across the table, the kind of rows. So these are colored in this way. We have period 1, 2, 3, 4, 5, 6, 7, and then lanthanides and actinides. I think this is generally the way most periods and periodic tables are organized. So 7 main periods and then kind of lanthanides and actinides in a separate section. So what happens in a period? Well, there's big shifts as you move through a period, okay? Moving across elements in a period will slowly indicate changes in metallic character, and we will learn what that means more today and in the next video. But on the left side, we have more metallic things, and on the right side, we have less metallic or non-metallic, and in the middle, we have that transition happening. Okay, so what's the history of this? Who discovered patterns among elements? I'm sure it was several people over several years, but in the 1800s, several scientists recognized similarities between some elements like calcium, strontium, barium have similar properties, chlorine, bromine, iodine have similar properties as well. So they began to organize them into groups. In 1869, the man in this picture here, Dmitry Mendeleev, organized the elements in order of increasing atomic weight, also in several layers, and leaving spaces where he expected undiscovered elements to appear. And this was really a genius thing that produced a periodic table very similar to the one that we have today. So this table was fairly accurate, predicted many new elements correctly in empty spaces. Oops. So a lot of people credit the modern periodic table with Mendeleev, and I think this opened the door for predicting many material properties and speeding up future discoveries. But it wasn't perfect at that time. So scientists later realized that it's actually more beneficial to arrange elements based on atomic number, which we now know is the number of protons in the nucleus. But scientists didn't even know that protons existed back in Mendeleev's time, right? Remember the Rutherford experiment in like the 1900s, early 1900s discovered that. So we now organize it based on atomic number, and there's not much difference between organizing the periodic table from atomic weight to atomic number, but if you do it by atomic weight, it will be a little bit different. You can actually go to the periodic table and find, I think, 2 or 3 locations where an element to the right of something has lower atomic mass, which is not what you would write if you were arranging it in order of increasing atomic weight or increasing atomic mass. So atomic number makes it a little bit better. Doing so generates the table and groups and columns we know today. Now there's group numbers, of course, I showed on a previous slide, but there's also recommended names for many of the groups. On the far left, group 1, we have alkali metals. Alkali generally means basic properties. So the reason that these are called alkali metals is because when they're mixed or reacted with water, they produce a basic solution. Number 2, similarly, is called alkaline earth metals. They'll also produce basic solution, and then earth metals, I'm not sure why, maybe they're found more in Earth's crust in their natural state. So those ones I would definitely recommend you remember. Group 15 is called pnictogens under nitrogen. This one I don't really think you need to seriously remember. I don't hear many people use this name at all and haven't seen it on the test. Number 16, chalcogens under oxygen. These ones also probably not that necessary to remember, but I think it is used more than pnictogens. 17 then, halogens, definitely remember this name. Halogens group 17 under fluorine. 18 then, noble gases, definitely remember that. Remember that most elements, when they either lose or gain electrons, go for a noble gas configuration. It means stable and sort of unchanging. So that's group 18 under helium. All right, periods then. So we call the rows of the periodic table the periods. There are 7 main periods on most periodic tables, and the period represents the highest occupied n quantum number. So way back in electron configurations, we talked a little bit about quantum mechanical labeling of things in the atom. So the main energy levels, level 1, level 2, level 3, level 4, and so on, are labeled with n. That's the principal quantum number. So the period also represents the principal energy level and principal quantum number that is being filled with electrons. Okay, so progressing through a period changes chemical properties of the elements. As you go left to right, things get less metallic. So we can sort of color the periodic table with metallic character as well, just in sort of 3 sections. There's things that we consider metals and quite metallic in blue. So actually most of the elements are fairly metallic on the periodic table. Then we have metalloids that are sort of in the transition between metals and nonmetals in the green. And then we have nonmetals in the orange, and also hydrogen in the top left. So less metallic character. So what do we mean when we say metallic character? What are metal properties? This is a bit of review from the metallic bonding section, but metals usually have these characteristics: good electrical conductors. Pure metals are a lattice of protons and a sea of delocalized electrons that can move relatively freely. And electricity is the movement of charged particles. Conductivity is the movement of charged particles. So we need delocalized electrons to conduct electricity. Metals are malleable. For similar reasons, metals can be reshaped with appropriate force. So the delocalized electrons mean that there's no sort of localized bonds that strictly hold atoms in place, but rather there are layers and things that can slide around for things with metallic character. Ductile, for similar reasons, metals can be pulled into thin wire shapes with tension forces, tensile forces. And lustrous, so when absorbing photons, electrons are free to move and oscillate in metallic bonding materials, and that allows sort of perfectly opposite waves to be emitted from those materials and give that reflective property. So this is what we would call metals and things with metallic character. So you can imagine nonmetals are the opposite of this. All right, so there are certain blocks that we also label on the periodic table, and this mostly has to do with the electron configuration and which suborbitals are being filled. So in the S block, we have the alkali metals and the alkaline earth metals on the left. This is where we would be filling up S orbitals, so S1, S2. In the middle, we have the transition metals and the D block. So the D block is everything here labeled in the green teal color. But the transition metals is from scandium to copper and everything underneath those. It does not include the zinc group. There's a special definition of transition metals that says there must be incomplete d orbitals that are not completely filled to be labeled a transition element. It's just a definition thing, but it means we don't include zinc in the word transition metals. Okay, and then we have the p block in blue on the right. This is where the p orbitals would be filling up. So p1, p2, p3, p4, p5, p6 from boron to neon and everything underneath. Helium is also belonging to the s block group. Because it's 1s2, right? It doesn't actually have any p electrons, even though it's a noble gas. We put it on the top right there. And there is the F block, which contains the lanthanides and actinides underneath the periodic table. But you can see it actually belongs sort of in the bottom left of the transition metals. These two rows could be inserted there, and they are on some very proper periodic tables, but because we don't want it to be super wide, we'd like it to fit on like an A4 size paper or poster or whatever, we generally cut those out and put them underneath just for, I guess, aesthetics and spacing. So we have some practice for the following positions on the periodic table. State the name, the group name, the principal quantum number, and the electron configuration. Okay, sorry, this is the periodic table, and starting with A, period 2, group 17, you can go check second row and the 17th column. That's going to be F. Name of that is fluorine. Try to spell it correctly with FLU instead of FLO. Okay, the group name is the halogens. Principal quantum number is the same as the period. So that's going to be 2. And the electron configuration then 1s2, 2s2, 2p5. It's one off the noble gas configuration of neon. That's good then. B, period 3, group 2. You can go check that out on the periodic table. I think you'll find that it is Mg. That is magnesium. And that has a special name, which is alkaline earth metal. Principal quantum number then, same as the period, that is 3. Electron configuration, 1s2, 2s2, I don't really know why I'm writing commas in these, you don't need to. So 1s2, 2s2, 2p6, and then 3s2. For an alkaline earth metal in period 3. All right, then C, period 4, group 8. A little more tricky, but you will find this one is Fe in the middle. That is iron. This doesn't have a specific name for group 8, but it is part of the transition metal larger group, so I'll write that. Principal quantum number is still the same as its period, that is 4. Then configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then finally the D, 3D is where it starts, 6 electrons in there. So that way we have 8 sort of valence. There's the 6 D electrons and the 2 4s1s, which explains why it's in group 8, 2 plus 6. Okay, that's enough of this. So that's the first section's done, 3.11 and 1.2. We'll move on to 3.13, which is to talk about trends in the periodic table a little more. So when talking about trends on the periodic table, we have a special word for it. It's periodicity. The fact that there will be trends of increasing or decreasing properties as you move around the table is periodicity. So periodicity is the idea that the periodic table predicts trends in various atomic properties. Position on the periodic table can be used to predict many things, including atomic radius, ionic radius, ionization energy, electron affinity, electronegativity, and others. So we will go through most of these things today. Starting with atomic radius. So atomic radius is really, if you think of the atom as a sphere, even though it might not be a perfect sphere, we can approximate it as such. Spheres can have a radius from the center point to the outside. What is that distance? So atomic radius, the trend is that it decreases across a period, and really it's left to right that we're talking about. So decrease across the period, left to right. And atomic radius increases down a group. So from the top of the group down to the bottom, atomic radius will be getting larger. Now this can be explained by electrostatic forces and shielding, which I'll talk about on the following slides, but you can just look at this graph. So we see there's a decrease in several sections, kind of going down here. Let me switch to red. Decrease, 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 decrease. So these generally represent going left to right through a period. This graph is atomic radius versus atomic number, so it's increasing as we go left to right. But it increases with the big jumps as we move to the next principal quantum number in the next period. So we have these big increases, which pushes the next section up overall. So these are sort of next period. Big jumps up. So that follows what's written on the right here. So how do we explain this? I mentioned that one of the causes of this is shielding. So what is electron shielding? This is the fact that inner electrons tend to shield outer electrons from the nucleus and from its electrostatic pull of attraction. So you can see we have a bunch of electrons here. Some are inner, some are outer. Looks like the reddish ones are inner and the green ones are outer. Now we have an attraction for the outer electrons into the center, into the nucleus, the red arrows, but then we have repulsion. We have electrons that are both negatively charged, they will repel each other, the blue arrows. So there's kind of a fight going on. The nucleus will pull them in a lot, but inner shell electrons will push them out. This is the idea of shielding, and shielding increases as there's more inner electrons, and there's more inner electrons as we go down the periods. So another diagram of this that expresses what we call effective nuclear charge. So of course there's a nuclear charge, it's set in the middle and it's constant, but the outer electrons will not feel the full pull of that because there's repelling happening from electrons underneath. The repelling vectors will push out and sort of counteract the pulling in vectors that try to attract the outer electrons. So no electron in higher energy levels actually feels the full positive charge of the nucleus. Instead, we have what we call the effective charge. It gets reduced by shielding. So there's a very general equation for this. Z effective, the effective nuclear charge, is equal to Z minus S. Z is the true nuclear charge, it's just how many protons are in the nucleus. And S is a shielding constant. It's just some number that reduces the effective charge. So here's an example. We have 11 protons in the nucleus in this diagram. The full charge Z is 11 plus 11, but the outer electron does not feel that. Its effective charge is approximated +1 to +2. Why is that? Well, there's 10 electrons, the blue electrons, in the inner shells that are trying to repel it, but they sort of have varying degrees of distance and position where they can affect this green electron, right? So it's an approximation that it will feel +1 or +2 attraction to the nucleus. We don't actually do this calculation in IB in high school, and we don't figure out how to find what the shielding constant is, but I think you do need to be able to explain this idea overall. So this explains why the radius increases as we go down the periodic table with more inner shells, inner energy levels filled up with electrons. So how about trends in atomic radius? Here are the trends represented in a little diagram. So radius obviously increasing as we go down a group and decreasing as we go from left to right. The decreasing is a fair bit more difficult to explain, but I'll give it a shot. So if we have a nucleus with some positive charge, we have maybe an inner shell with 2 electrons. I'm drawing a planetary model here, and some of the slides I have are showing planetary model. Even though we know it's not perfectly true, it's certainly helpful to picture things and explain things sometimes. So maybe we have another shell starting. So what happens when we sort of go left to right across the periodic table? We will be adding more positive charge into the nucleus because atomic number goes up left to right across the table. So that means outer electrons start to feel more attraction. When they feel more attraction, they're going to actually be held closer, and that decreases the radius. But you can argue, well, atoms are neutral. So as we move left to right, we do get more positive charge in the nucleus, but we also get more electrons. And this should increase repulsion. And you might say you expect it to increase repulsion equally, and therefore radius should be fairly constant. But it turns out that adding electrons into the same principal quantum number does not really have the same shielding and repelling effects as having electrons in inner shells, okay? Inner shells will definitely affect and repel things nearby, but adding things into the same principal quantum number, this outer shell, this electron doesn't really have that much effect on the electron in the same level that's sort of far away from it. Now, I know, again, the planetary model doesn't actually express these distances well at all, or the position of these electrons, but it's something that you can use in your mind and use to explain, I think, even on IB exams, to explain why putting electrons in the same outer shell, principal quantum number, principal level, does not create as much repulsion as putting them directly in between electrons and the nucleus. Positioning really matters. Okay, hopefully that made some sense. So overall, we will see radius decrease as we go left to right, more protons in the nucleus, but electrons are being added to the same outer shell. As soon as you add a new shell though, which means you have more inner electron shells, then radius will have a big increase, a big jump that was shown on the graphs that I showed a couple slides ago. Okay, so this is atomic radius. What about ionic radius? Starting with cations, positive things. If we remove an electron, well, the trend is exactly the same, but you'll notice I've tried to shrink this image a little bit, and that's because cations are smaller. They're just smaller radius than the normal elements, but the trend is the same. It increases going down a group and decreases going left to right across a period. And the explanation for this is the same as atomic radius. And what about anion radius, negative ions? Same trend again, it's just everything's bigger. I tried to expand this image a little bit. Anions are larger. As you gain electrons, you get more repulsion. Things push each other farther apart. So anions are larger than their base element. Okay, so let's try to explain this. Cation radius always decreases compared to its pure element. So we have potassium atom. It has this radius 220 and this configuration, 19 protons, 19 electrons. If we remove an electron, we're actually going down a principal quantum number, and just removing an electron overall decreases the overall repulsion and repelling happening within the atom. So everything can get kind of closer together. We get a smaller cation, K+. So that radius is only 138. It's almost half. That's a huge difference. But that's what removing, the outer shell, going from period 3 kind of back to period 2 can do. Let's consider then anion. Here is 9 protons, 9 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this will be fluorine F. It has 64 picometer radius, but as it gains an electron, that radius increases a lot, more than double, to 133. We get F minus. So adding an electron increases the repelling going on. Everything repels each other a little bit more and has to expand and sort of open up to accommodate those forces. So F minus given here. So we can also show comparisons of several groups. So we have the alkali metals, alkaline earth metals, 1, group 13, aluminum metal, and then the non-metal halogens from fluorine to iodine. You can see the cations are always smaller than their base element, and the anions always larger. One of these, the Br, should not have a minus, just ignore that. Generated with ChatGPT, but I think it's pretty good. So we can also talk about isoelectronic species. You might remember this from my electron configuration video if you watched it. So certain atoms and ions can have the same electron configuration. Even if they have different protons in the nucleus, they will then have different overall charge, but a similar electron configuration means that they'll have similar chemical properties. So we've got oxide, O2 minus. We've got fluoride, F minus, sodium, Na plus, magnesium, Mg2 plus, neon, neutral atom. All of these have the same electron configuration. That's 2s1, 2s2, 2p6. So a filled level 1 and a filled level 2. This means that they're all fairly stable, and these are all fairly common versions of this element or ion to exist. They will have some different properties, of course, though. You can see the radius varies significantly, and the charge. So electric charge is pretty important. It determines how things will flow in an electric field, what regions of other molecules they'll be attracted to. So that can definitely affect their chemistry and position. But their overall stability for these things are very stable. So that's a similarity. Okay, what about ionization energy, abbreviated as IE? Ionization, hopefully you should know, means creating an ion, but specifically we're creating a cation in these examples. So ionization is to remove an electron, and we can have different numbers of ionization energies. So IE1 or E1 is removal of 1 electron. IE or E2 is the second removal of an electron to make a 2 plus thing. And in general, N, so An minus 1 plus to An plus is the nth ionization energy. You can label it that way. And this can go on until there's no more electrons left in the atom, obviously. So hydrogen doesn't have a second or an nth ionization energy. It just has the first one. Helium would only have 2, and so on. Just keep that in mind. Also, a little note here, this is for gas phase atoms and ions. So this will be a set amount of energy required to do this, and it's a little bit different for gases, liquids, and solids. So our official definition and standard one that we use is for gas phase elements and ions. So there are trends in ionization energy as well. The energy required to remove 1 mole of electrons from 1 mole of gaseous elements. So here's an example. N is just some element. So M gas goes to M gas plus an electron. Let's see the trend in these. So you can see the purple color is going to be a low ionization energy value, and the more green yellowish will be higher. So this is sort of how the ionization energies go on the periodic table. They're very low on the left and at the bottom, but much higher around the top right side and including hydrogen on the top left. And the transition metal area sort of has its own trends within it, but we're more focusing on the general trends across the whole periodic table in IB here. So the general trend of this is diagonal arrow you can think of. So ionization energy increases as you go bottom to top and increases as you go left to right on the periodic table. That will create this green arrow trend. We can also show a graph of this. Again, fairly clearly shows increases as we go left to right through a period. However, the ionization energy decreases actually overall as we go down the periodic table to following periods in this way. So that would be sort of next period. So it's important to keep these sort of trends in mind. Another thing you might notice is that the highest points here would be the noble gases labeled with stars. So they generally have the highest ionization energy in their period, which makes sense. They already have a stable structure. So removing an electron would cause instability, and that causes quite a bit of energy to produce that unstable state. Conversely, the alkali metals are the lowest. They only need to lose one electron to become a stable noble gas configuration, so they have the lowest ionization energy. And this graph only shows the first ionization energies. So how do we explain the ionization energy trend? It's essentially the opposite trend as ionic radii, but for nearly the exact same reasons with shielding and nuclear charge. So going left to right, more protons in the nucleus pull the outer electrons closer. That makes it require more energy to remove them. You might remember the electrostatic force Fe is proportional to 1 over r squared. Proportional sign. So as distance decreases, the force will get stronger. You would need to put in more energy to remove the electrons as they get pulled closer to the nucleus. What else? Okay, so going down into the next period introduces a new layer of shielding of inner electrons filled up levels. So that greatly reduces the ionization energy because outer electrons become more weakly held, lower effective nuclear charge, more repelling from inner electrons. All right, very important to know. Another idea here is electron affinity. This is the opposite of ionization energy. This is how we would make anions. We would add an electron to some element. Our standard definition here has in the gas phase, so 1 mole of atoms when 1 mole of electrons in the gaseous state is added. I should mention for the ionization energy as well, everything is defined for 1 mole. So removing 1 mole of electrons from 1 mole of element is the ionization energy. But here's the affinity, adding an electron. So an example would be fluorine gas plus 1 mole of electrons goes to 1 mole of F minus anions. In that specific example, it's minus 328. The minus indicates energy is released when this happens. And this is usually the case, it's exothermic. So that's pretty important to remember. When we talk about high electron affinity, we're talking about the size of this number, even though it's getting more and more negative. So just keep that in mind. So let's see another periodic table with the 3D version of electron affinities shown. So it looks like red and gray is low, and green and blue teal color is higher. So it's really more all over the place than some of the other trends we've seen. But overall, hopefully you can see going from left to right will be an increase in electron affinity. With some major exceptions, these little gray areas will actually either be zero, meaning energy is not released at all when you would try to add an electron to this system, or it could even be positive, and that means you would have to add energy to force an electron onto this atom. So I think electron affinity can be positive, zero, or negative. Most of them are negative. Most atoms would want to gain some electrons, but some of them, like you can see where nitrogen would be here in the top right, or some of the noble gases, all the noble gases actually, they don't tend to accept electrons and release energy by doing so. So the general trend here is there's an increase left to right, but through a group, it's really difficult to say. It's up and down, and no real visible trend is obvious. And there's a lot more exceptions with electron affinity. So as usual, here's a graph. It generally just shows the increase left to right as we go up these big peaks, but sort of across these peaks, the trend is not really known. It's up and down, up and down. So that's a representation of what I just showed on the previous slide and talked about a little bit. So again, the trend is opposite to ionic radius, if you consider it. Going left to right across the period increases electron affinity, but there's no real trend going down a group that can be seen. So sort of these three increasing arrows do represent increases, but the one across the top, which would be going down groups, is unclear. Okay. Moving on. Electronegativity. This is actually 100% review if you've watched my videos on like covalent and ionic bonding. But just to refresh, it's also part of periodic trends. So this is written as XP or chi, P, the Greek letter for the Pauling scale of electronegativity. There are different scales, but what we use in IB and what I think most conventions use is this Pauling scale. This is defined as the relative attraction that an atom has for electrons in a shared bond and defined through covalent bonding. So here's an example, HF, hydrogen fluoride. In this bond, the pair of electrons that makes the covalent bond is not shared equally. Fluorine pulls those electrons and that density closer to itself. So it's more orange-yellow color in this that represents higher electron density, whereas H loses electron density and goes low. So we define H as having lower electronegativity as F. And this can happen in almost every type of bond, covalent bond. So in other words, when an atom is sharing electrons, how much electron density is taken or conceded to the other atom? So we have a scale for this that goes from 0, or maybe like 0.7 or something, up to 4. So 4 is the highest, the most electronegative, and under 1.5 is least. So the highest ones are generally in the top right of the periodic table: nitrogen, oxygen, fluorine, and Cl, with F being the highest. Then from 2 to 2.9, we have other nonmetals and metalloids from 1.5 to 1.9, and then metals generally under 1.5. So these are all in section 9 of the data book. I'd recommend you become very familiar with that. You're going to use it a lot. And I've showed this before as well, this periodic table 3D version with electronegativities for each element. So it's high in the top right near fluorine, but not including the noble gases, right? And it's low in the bottom left near like francium and cesium, the orange colors, yellow colors. And then sort of mid through the middle of the periodic table in the green section. Okay. So that general trend also goes bottom left to top right, an increase in that way. So going up a group increases and going left to right through a period increases. With some exceptions, but okay. In summary, we can have this periodic table with all the trends shown on it: ionization energy and electronegativity, and electron affinity increase left to right. Atomic radius decreases from left to right. Ionization energy and electronegativity increase from bottom to top. Atomic radius increases top to bottom. So I'd say you generally have to remember these, memorize them, be able to explain them. So some points, the atomic radius trend also includes ionic radiuses like cations and anions. And the noble gases have no electron affinity, so even though it goes left to right increase, there's a hard stop at the noble gases. They don't have electron affinity. And generally we can't measure electronegativity for them as well because they don't form covalent bonds. All right, so the final thing today is a little bit of practice. So we have a table here with different trend properties, and we want to know which of this pair has the highest magnitude or number size of these properties. So magnesium or calcium. Let's start with that. Atomic radius should be calcium. Let me switch to red. Why calcium? It's underneath magnesium within the same group. That trend increases. Ionic radius should also be calcium. That trend increases down the periodic table as well. As long as we are talking about the same type of ion. So magnesium and calcium will both be cations, go 1 or 2 plus. But calcium is still underneath magnesium, so it should still be larger. Electron affinity, this is a challenge. We actually can't know this directly from trends. Remember that there's no real trend for electron affinity up or down the periodic table. So you have to look this up. And it turns out the answer, I think, would be calcium. It's very slightly exothermic and favorable to gaining an electron. I think it's like 2 kilojoule per mole or something, whereas magnesium is a hard 0. So that one you'd have to look up. Ionization energy, magnesium is higher because it's higher on the periodic table, less shielding. Electronegativity, magnesium higher. Next, strontium and iodine. Atomic radius will actually be strontium. These are in the same period. Period 1, 2, 3, 4, 5. So iodine having more protons in the nucleus can pull things closer. Strontium has less. Ionic radius, though, this is where you have to think pretty hard. Strontium, when it becomes an ion, will lose electrons, become a cation, get smaller. Iodine, when it becomes an ion, gains an electron to get its nearby stable noble gas configuration. It will get larger. So because of that difference, I'm going to predict iodine's radius to be larger for ionic. Electron affinity, iodine needs electrons more. Ionization energy, the energy required to remove an electron for iodine would be fairly high. Electronegativity, iodine higher than strontium. Just follow the trends that I showed in the previous slide, and that should explain most of these. Except for ionic radius, you have to think a little bit harder. Okay, carbon or silicon? Atomic radius will be silicon, it's underneath. Ionic radius, also silicon. I think we can assume both of these will become cations and lose some electrons, although they really could maybe go both directions. We'll assume that they both go the same direction here. Electron affinity though, carbon, ionization energy, carbon, electronegativity, carbon. Carbon generally wants to hold and gain electrons more than silicon. Okay, barium or chlorine, atomic radius, barium. It is farther down the periodic table, and it's also left, so there's no way that chlorine could be larger. Ionic radius though, kind of have to think hard again. You don't know this just from looking at trends because they're sort of opposite. But if you look it up, chlorine, Cl-, when it becomes an anion, will have the larger radius. Electron affinity, definitely chlorine though. Ionization energy, definitely chlorine. Electronegativity, definitely chlorine. Chlorine wants to gain and hold electrons much more than barium. Next, lithium or fluorine. Atomic radius will be lithium. These are both in the same period, period 2, but lithium is left. Ionic radius, this will be fluorine. As it gains electrons, it expands significantly, more than double size. So we can predict fluorine anion will be larger than lithium cation. Lithium loses electrons, remember. Then electron affinity, definitely fluorine. Ionization energy, fluorine. Electronegativity, fluorine. Next, K or Br, potassium or bromine. Atomic radius will be potassium. These are in the same period, period 1, 2, 3, 4. But K is on the left. Ionic radius, for the same reason as lithium and fluorine, Br, as it gains electrons, will gain significant size and become larger than potassium cation that gets smaller. Electron affinity, definitely Br, ionization energy, Br, electronegativity, Br. Okay, carbon or lead, C or Pb. Atomic radius, Pb, it's much lower on the periodic table. There's a lot of shielding going on underneath. Ionic radius, for the same reason, it's going to expand. Electron affinity though, carbon. Ionization energy, carbon. Electronegativity, carbon. Follow the trends for a group. Next, cesium or fluorine, last one. These are both in, cesium is in group 1, fluorine group 17. So atomic radius, definitely cesium. It's left and underneath. Ionic radius, pretty hard to say. When they become ions, cesium gets smaller, but fluorine gets bigger. How much is difficult to say, so you have to look this up. But cesium is so low and so massive, it's still going to be larger if you look it up. Electron affinity then, fluorine, ionization energy, fluorine, electronegativity, fluorine. And then we're done. So hopefully you can see that generally electron affinity, ionization energy, and electronegativity have similarities. The same element will have the larger amount when comparing like this. But ionic radius, you really have to think what becomes a cation, what becomes an anion, and you might have to look up specific data to really know. All right, so that's all for today. Next time we'll talk more about metallic character and reactivity throughout the periodic table. Thanks for listening. Hope you learned something. See you next time.